The concept of a PulseJet engine has been around for a very long time. It wasn't until the late 1800s that it started to gain momentum. The first working PulseJet engine was created and patented in 1906 by a Russian engineer. Sometime after that, in 1931, Robert Goddard designed his own PulseJet engine, and to demonstrate it, he attached it to a bicycle to show the public how the propulsion works. Soon after that, an engineer, Paul Schmidt in Germany, designed his own version of the PulseJet. His was more efficient than anything that had been seen by the way that he had developed the valve and intake system. Soon after the design, World War II had started. The Nazi Party was looking for any kind of technology to use against its enemies. This is where the PulseJet engine came into play. They attached the V1 to what they called the buzz bomb that they used to bomb its neighboring territories.
The PulseJet-powered cruise missile V1 preceded the V2, a liquid-fueled ballistic missile, which was widely known to be the start of modern rocketry. Without the V1 or the V2, we wouldn't have the advancements we have now in modern rocketry propulsion systems.
Liftoff of Falcon 9. Falcon 9 is cleared to... First stage propulsion is nominal. Stage separation.
What we want to do is recognize that there are two separate systems. So when we have system 1, that is the combustion chamber. And system 2 is the exhaust port. So the main things that are occurring are the initial ignition, and then also the steady state that it reaches once it's self-propelling and self-igniting. So if you want to look at it like two separate phases, you have in minus E out equals delta E of system 1, and phase 1 being the initial ignition, when we have to light the fuel and pump in air simultaneously to get it going. And we want to branch that out. Q in plus work in plus mass of the air in plus mass of the fuel in. We have Q out, mass out. And all the mass that is leaving, we can consider exhaust. There's no work. Heat in is when we light the fuel with a lighter or butane torch or something like that. And we have it over here because this is where the lighter is, but technically speaking, this Q in is actually for a combustion chamber. So Q in, we have the mass coming in spaced off the diameters and the velocity. We don't have to consider potential energy. That's the enthalpic energy of the fuel in, minus the heat that will radiate out of the combustion chamber and pretty much this entire thing, because it's going to be really, really hot, minus the mass of the exhaust out times its kinetic energy squared plus its enthalpic energy equals the change in energy of system 1. Now, technically speaking, all the mass that goes in is the exact same as all the mass that goes out. So when trying to completely simplify this to understand everything that's going out, you can technically cancel it. But for the sake of any sort of calculations for temperature or pressure or velocities, we kept the masses in to break them down. But technically speaking, when it's all said and done, all it is just the heat that we provided in minus the heat that loses is the change in energy of the system. And then phase 2 would pretty much just come out to be the exact same thing. Because at that point, the PulseJet engine is maintaining its ignition because the differential in pressure will then cause air to continuously suck in to fill in that vacuum, in a sense of lack of pressure. And then because we are continuously pumping the same amount of fuel in, and because it's already technically on fire, it'll continue to be on fire. And then thrust will then allow the engine to move forward. And then I'll just move you down. I'll work you down here. So when looking at the exhaust port, it's phase 1. Basically come out to be very similar because what we have going on here is no heat in, no work in. Just say mass. The exhaust from the combustion chamber is the mass that is in here. We have it basically transferring across these two system boundaries because whatever leaves the combustion chamber is the mass that's going to go in here. And then, of course, negligible mass that's being sucked in from there. But minus heat out. Minus work out. Minus mass out. Like we said, no Q in, no work in, no work out. And so mass in for the exhaust, which is the equivalent of the mass into the air, mass into the fuel of system 1 times its velocity, which would be the same that comes from the mass out exhaust from system 1 plus its enthalpic energy squared. Also being the exact same. Minus the heat that's radiating out from the body, minus whatever mass is leaving out, providing the thrust. So its velocity is going to be very needed. Is
So I'm Javier Gomez, and today I'll be working on the entropy balance for our PulseJet engine. So we're going to be focusing on the first system, which is the combustion chamber. So we'll start our entropy balance. S in, S out, plus S in is equal to the system, right? Plus the mass in, right, of the air coming into the combustion chamber, plus entropy, plus, right, we have in the combustion chamber we have the air coming in, plus the fuel that we have propane. Out, right? So again, we're only focusing on the first system. So the Q out we're gonna, since it comes out, right? Both masses that came in by the air and the fuel, this actually comes out to be the exhaust. So we'll rewrite this part.
Please take care. So we do have a compressor for us. Just needs a little bit of